Hey folks, welcome to another set of Intro Chemistry video notes. In today's lesson, we're going to talk about covalent bonding and naming. For this lesson, the last lesson, and the next lesson, we're going to be covering the same standard. Let's get started. Just a quick reminder, because this is extremely important for covalent bonding, valence electrons are those electrons in the highest principal energy level. These electrons are the only electrons that participate in chemical bonding. The goal of almost all atoms is to end up with 8 valence electrons, or look like a noble gas. In the last lesson, we learned about ionic bonding and how atoms will lose electrons and others will gain electrons in order to get to that magic number 8. In this lesson, we're going to learn how some atoms, instead of transferring those valence electrons, will just share their valence electrons together so that everyone gets 8 valence electrons. So, a chemical bond is just some kind of force that holds atoms together in a molecular compound. When talking about ionic bonding, that force was the electrostatic forces of attraction between positive and negative ions. When it comes to covalent bonding, the force is the attraction of 2 nuclei to a pair of electrons shared between them. Neither atom becomes fully positive or negatively charged, as they don't lose or gain any electrons. Essentially, when we draw our Lewis symbols for atoms, those unpaired electrons in one atom will find a partner by pairing up with unpaired electrons from another atom. Those 2 electrons shared between 2 atoms is called a covalent bond. When we have 2 or more atoms held together with covalent bonds, we call that a molecule. And when we have a substance made of molecules, we call that a molecular compound or molecular substance. Again, covalent bonds are just pairs of electrons shared between 2 atoms. This generally only occurs between 2 nonmetal atoms. This is because nonmetals all have relatively high electronegativities compared to the metals. So, they all pull shared electrons closer to their nucleus with a lot of strength. As such, neither atom is willing to release any of its valence electrons. So the 2 atoms end up holding on to the same pair of electrons together. For example, here is carbon dioxide. The Lewis symbols for these atoms look like this. Carbon has 4 unpaired electrons, and each oxygen has 6 valence electrons. 2 of them are unpaired. Therefore, they can move around to pair up those unpaired electrons together, creating the carbon dioxide molecule we all know and love. We can also represent shared pairs of electrons with a line. That line is a covalent bond, which represents those 2 electrons. The transfer or sharing of electrons actually exists on a spectrum. The more electrons get transferred, the more ionic the bond is. The more the electrons get shared equally between the 2 atoms, the more purely covalent the bond is. You can think of atoms in a covalent bond as playing a tug of war with the shared electrons. If they have the same electronegativity, they pull on those electrons with the same strength, and they end up smack dab in the middle, not shared to one side or the other unequally. When this happens, we say that they get shared equally. If they have different electronegativities, the one with the higher electronegativity will pull electrons toward it more and will become partially negative, because the negative electrons are closer to it, while the other atom gets partially positive because the negative electrons are further away from it. And if the electronegativities are so vastly different, as they often are when one atom is a metal and the other is a nonmetal, the one with the higher electronegativity will completely pull the electrons away from the other one and create negative and positive ions. So, when electrons are transferred, it's an ionic bond. When electrons are shared, but not evenly, it's a polar covalent bond, and each atom has partial negative or positive charge. The lowercase Greek letter delta, with a negative or positive sign next to it, is how we represent partial charges. We call these polar bonds because they have 2 sides to them, a positive side and a negative side. And lastly, if the electrons are shared perfectly evenly, neither atom gets a partial positive or negative charge. We call it a pure covalent bond, or a nonpolar covalent bond. Here's a quick summary of how we determine what type of bond we're looking at. Automatically, if it's a metal paired with a nonmetal, we assume it's an ionic bond. If it's 2 nonmetals, we assume it's a type of covalent bond. If we look at a chart of electronegativity values, which range from 0.7 to 4, The difference in electronegativity values between those two atoms will tell us if it's polar or not. Basically, if there's no difference at all, or a very slight difference, less than 0.4, we consider it essentially nonpolar. If there's a difference of 0.4 or larger, we consider it polar. The larger the difference in electronegativity, the more unequally the electrons get shared between the atoms, and the larger the partial charges in the atoms will be. Now, the interesting thing about covalent molecules is that they can happen in a variety of ratios. By that, I mean we can have things like CO or CO2, or H2O or H2O2. Unlike ionic compounds, which form in predictable ratios all of the time due to their charges, making them super easy to name, we have to take extra steps when naming covalent molecules. What that means, though, is that writing formulas for covalent compounds is way easier because we don't have to worry about canceling out any charges. To name covalent molecules, all you have to do is name the elements in the same order they appear in the formula, change the ending of the second element's name to "ide," just like we did before, and then add a prefix before each of those element names that represents how many atoms of that element there are in the molecular formula. The prefixes are listed here. The only weird rule is that when there's only one atom of the first element, we don't have to put the mono prefix. Otherwise, you will use prefixes for both parts of the name. So we could have CO2, which would be called carbon dioxide, or CO, which would be called carbon monoxide. The di and mono prefixes tell us there are 2 and 1 oxygens respectively. Writing the formulas is super simple. You just have to write down the element symbols in the same order they're written in the name. Then, if the element has a prefix, we just turn that into a subscript. For example, dinitrogen pentoxide would be N and O, but the name tells us there are 2 N's and 5 O's because di and penta. So we put N2O5. To draw molecules, there are a few steps we need to follow. Step 1. Count up the total number of valence electrons you have to work with. Do this by adding up the valence electrons for each element based on the periodic table. Then draw the skeletal structure of your molecule. This is done by writing the symbol for the element with the least electronegativity, but never hydrogen, and then connecting the other elements around it with covalent bonds. The one with the least electronegativity that we put in the middle we call the central atom. Each line or bond you just drew represents 2 of those valence electrons, so subtract that total from your total number of valence electrons. Then you place the remaining electrons around the outer atoms until you run out. There are some more specific rules that go with that, but essentially the goal is to have the correct number of valence electrons and have every atom with 8 valence electrons around it, except for hydrogen, which only ever wants 2. If you have placed all your electrons and you have atoms that don't have 8 around them, you can move those electrons around to create double or triple bonds. Let's do a quick example. Carbon dioxide, as we saw before, has 1 C and 2 O's. Carbon comes with 4 valence electrons, and oxygen comes with 6. So we get 4 plus 6 is a total of 16 valence electrons. We're going to start by writing C for carbon in the middle, and then we'll draw the O's on the outside and connect them with covalent bonds. At this point, we've used 2 and 4 valence electrons, 2 for each bond. That leaves us with, from 16 minus 4 is 12. We'll place those 12 electrons on the oxygen because they're more electronegative and would rather hold on to those electrons. So then it looks like this. At this point, we've placed all 16 of our valence electrons, and the O's are happy with 8 valence electrons around them. But the carbon only has 4. If one of the oxygens shares one of its lone pair of electrons with carbon, then we would create a double bond there. Now the carbon has 6, that oxygen still has 8, so it's still happy. To get 8 on carbon, we could either pull 2 more from that same oxygen and create a triple bond, or since nature likes symmetry, we can pull 2 from the other oxygen and create a second double bond. Now all atoms have 8 valence electrons, we have 16 total, and everybody is happy. We'll do plenty of examples of this in class and take our time learning how to do it correctly. The most important thing is that you follow these steps one at a time and do your very best to learn how to do it. The more we practice with it, the easier it'll become. That's all for today, folks. As always, if you have any questions, ask.